Hello Pre-Calc BC and happy snow day. Today we are going to be talking about simulating motion. You are going to need your calculator quite extensively through this lesson, and we will be moving back and forth between both function mode and parametric mode. Function mode is your normal mode for your calculator. So all right, let's go ahead and just quickly revisit these formulas that we're going to be using today. The first two formulas we will be using on the first page, and then the second two formulas we will be using on the back. Today we will only be doing problems 1, 2, 3, and 5. We are skipping 4. All right, so number 1, we have Maggie throws a ball straight up with initial speed of 40 feet per second from a height of 5 feet. The fact that she's throwing the ball straight up means that the angle she's throwing the ball at is 90 degrees. Her initial speed, this will be her initial velocity. And notice the units, we are at feet per second and a height of 5 feet. So that's her starting height. So the first part here, we have find parametric equations that describe the motion of the ball as a function of time. So your parametric equations are always an x equals and a y equals. So our x equals, we have v theta cosine theta, v sub 0 cosine theta, all multiplied by t. Notice how you have parentheses around the v cosine theta. We want to make sure we're multiplying that whole value by t, not just taking cosine of theta t, if that makes sense. So x is going to be 40, cosine theta is 90 times t. And you can go ahead and simplify that. Cosine of 90 is just 0, so this is 0 times t, or 0. And then y equals, we have this equation, 1/2 at squared. A is our acceleration due to gravity, and since we are in feet, we're going to use this negative 32. Plus v sine theta multiplied by t, plus your starting height, which is 5. Okay, so here's your first one, and I'm going to simplify that as well. 1/2 of negative 32 is negative 16. 40 sine, whoops, I forgot to change my theta to a 90. Sine of 90 is just 1, so this is plus 40t plus 5. All right, so there you go. Those two blue are your parametric equations. Part B, how long is the ball in the air? Well, the ball is in the air until it hits the ground. And when it hits the ground, your vertical distance, or your y value, would have to be 0. So in order to figure out when our ball, or how long the ball is in the air, we're just going to set our negative 16t squared plus 40t plus 5 equal to 0. And we're just going to graph that with function mode. And you might have to change your window a little bit here. I think I'm at a 50 for my y max. So we're looking for this location right here. That's where it's going to hit the ground, and so we'll know how long it was in the air. You are going to have to put a 0 in for y2 because then we'll be able to find our intersection. So second trace 5. And come over here. Enter, enter, enter. Okay, so that's about 2.619 seconds. Part C, when is the ball at its maximum height? Determine the maximum height of the ball. So again, you're just dealing with this exact same graph. Its maximum height would be the biggest y value that you get, so your max right up here, and that will give you both the time and the y coordinate, which will represent the height. So we'll go ahead and find the max. Your calculator is way faster than mine. So 1.25 comma 30. So remember, this is t and this is y, so that's saying at 1.25 seconds the ball is at its max height of 30 feet. All right. Part D, simulate the motion of the ball by graphing the equations found in Part A. So you don't have to write anything down for this. I'm just going to show you how to use parametric mode. This one isn't very exciting, to be honest. So we're just going to type in 0. Because remember, the ball just got thrown straight up in the air. It didn't move left or right at all. So that's why x is just 0. And your y was negative 16x squared, or t squared, plus 40t plus 5. For your window, I moved my t-step to 0.005. I thought 0.01, which is what we would normally do, is just a little too fast. I'm going to go from 0 to 5 seconds because if you remember, it hits the ground at 2.619 seconds, so there's not really anything going on after that. Oh, I didn't mean to do that. And then what else? Y max I put up at 50 because the highest that the ball gets is 30, so I just left it what it was before. So the ball goes up and it comes back down. And notice it goes past the y or the x-axis because we have this going for 5 seconds, and your calculator doesn't understand that the ball would hit the ground and then just stop, so it's burrowing into the earth. If you go ahead and you change your Tmax to 2.619 seconds, it would stop right at the x-axis. See? Because then that's where it hit the ground. So you just have to change your t to see like how much of the picture you actually get. Cool. All right, let's go on to the next question. Kate throws a baseball with an initial velocity of 10 meters per second from a height of 4 meters at an angle of 45 degrees. Notice you have new units. So there's your starting height. There's theta. Parametric equations are always x equals and y equals. So v cosine theta times t. V cosine theta times t, which is 5 root 2t. And then your y is negative at squared, or excuse me, negative 1/2 at squared. Technically 1/2 at squared, but your a is always negative. A is going to be, since we're in meters per second, negative 9.8. So 1/2 at squared plus v sine theta times t plus the starting height, which was 4. And so that's going to be a negative 4.9 t squared plus 5 root 2 t plus 4. Part B, how long is the ball in the air? So again, the ball hits the ground when the vertical distance is 0. So we're going to go back to function mode, and we're just going to graph the y, because the y is talking about vertical distance. That's going to be the one that tells us when we hit the ground. X is just telling you how far across you go. So like when the ball gets thrown versus when it hits the ground, horizontally, how far did it go? That's not going to tell us when it actually hits the ground. Hitting the ground is a vertical distance, so we want to graph the y. Oops, careful, don't do that. Oops, still don't do that. Okay, right there. I still have my y equals 0. All right, so 1.878 seconds. Part C, find the horizontal distance traveled by the ball. So, all right, I think this is pretty cool. You just figured out that 1.878 seconds is how long it takes to hit the ground. So basically we're saying horizontally, how far did the ball go in that time? So all you're going to do is take this guy and you're going to plug it into t in your x equation. So this will tell you at that time how far did it go. You are going to want to use the full decimal, which I know the real decimal wasn't very long, but actually if you press X, you'll see it's a little bit longer than what was on there. And when you multiply by the 5 or 2, you should get this value, 13.278. And that is in meters. So that's how far it traveled horizontally, which I think is pretty cool. But again, I'm a math teacher. All right, so next we're going to flip the page. We are going to do 2 more problems, and this time we're going to use the equations. Is it d equals? What did it say? Yeah, d equals 1/2 at squared, and d equals rate times time. So both questions 3 and 5 don't have to do with throwing anything. It has to do with just regular motion. You're running or walking, along the ground. So there's no y component. But because we're going to be dealing with parametrics, we are going to have to still have a y equals equation. We'll get to that in a minute. So catching a bus. Darsh's bus leaves at 5:30 a.m. and accelerates at a rate of 3 meters per second. Okay, so Darsh's bus is accelerating. That would be your a value. Darsh, who can run at 5 meters per second, arrives at the bus stop 2 seconds after the bus has left. Oh, this is very upsetting. It's a tragedy. So, all right, that's Darsh's rate. All right, let's talk about this arrives 2 seconds after the bus has left, because this can be confusing for people. What that means is we're not going to be able to use just t to represent Darsh's time, because Darsh has not been traveling for the same amount of time that the bus has. So we're going to have to see what to do with that. To start though, let's worry about the bus. Parametric equations that describe the motion of the bus and Darsh. All right. I'm putting x1 and y1 because we are also going to have to deal with Darsh, and he is going to be x2 and y2. Okay, so x is really this because his distance is traveling, or his distance is in the x direction. So we have 1/2 at squared, where a is 3 meters per second. For y1, the only purpose of this is that when we graph it parametrically, it is going to show us both the bus and Darsh's graph at different levels. So we want to give a number to show how high up we want his graph to be. It doesn't really matter how high up you want it to be. I would not put 0 because then you're on top of the x-axis. It's going to be harder to see what's going on. So I'm just going to put a 1. For Darsh's, we're going to want his to be up a little higher. We don't want them right on top of each other, then you're not going to be able to see what's going on. So I'm going to put his at like 3 or 4. Okay, again, you have choice here. It just is visually so you can see how high up they are. It'll make more sense once we actually graph it. So, all right, now let's talk about how far Darsh runs. So we know distance is equal to rate times time, and his rate is 5. Okay. However, we cannot put 5t because Darsh showed up 2 seconds later. Okay, so t is representing how much time the bus has been traveling. Darsh didn't get there until 2 seconds later, which meant he traveled 2 less seconds than the bus. So 2 less seconds would be t minus 2. Think of it this way. If I've been running for 5 minutes and you start running 2 minutes after me, you've been running for 3 minutes, right? Because I ran for 5, you started 2 minutes later, and we're saying we stopped at the same time. You would have been running for 3 seconds or 3 minutes. So we just take the bus's time and we subtract 2 from it. All right, so these are your parametric equations right there, this whole thing. Part B, determine algebraically whether Darsh will catch the bus. If so, when? So basically, if they're going to catch the bus, or if he's going to catch the bus, these two equations would have to be equal to each other. Okay, or think of them as intersecting. It does not mean that Darsh is hit by the bus if they intersect. It means that Darsh reached the location where the bus is. All right, this is not a tragedy in that sense, okay? No one gets injured in this math problem. This is not like Melissa and her rocket ship that crashed into Mars from first semester, okay? Everyone is fine. So we're just going to set these two equal to each other. And if you want, you can move everything over to one side, but I'm just not going to deal with that. I'm just going to graph them like this. So 1.5x squared, and it was, what was 5x minus 10. And when you graph that, you notice that this line and this parabola are never going to intersect, which means, alas, Darsh, you did not catch the bus. You're going to have to walk, I guess. So no. If they did intersect, your intersection point would tell you at what time he caught the bus. Okay. All right, here's the fun part. Simulate the motion of the bus and Darsh by graphing the equations found in part A. So we need to go to parametric mode. And we're going to type them in. 1.5t squared, and we're putting him at 1. That's the bus. 5t minus 10. We're going to put Darsh at 3. I think that looks good. Window. All right, so what we're going to do is we can do for time. Let's go for 10 seconds. T-step will keep the same. X min, we're going to start at 0. X max, that's how far he actually traveled. Let's make that like, I don't know, 50. And the y min, we don't need to see that much because your y, we went from 1 to 3, so I'm just going to do that. We are also going to do one more thing. Don't press graph yet. We're going to go to simultaneous mode. So you actually didn't even know this existed. But right now you're in sequential mode. What that means is it graphs one line and then it graphs the other. Simultaneous mode means that it's going to graph both lines at once. What? Okay, and we might have to change our window because I didn't have written down what my window was, so I'm just punting. So now let's graph. All right, so this is the bus. 2 seconds later, Darsh leaves. Oh, yeah, and you're going to notice that the bus is like, peace out. So sorry, Darsh, you're not going to catch that bus. Very sad. This stopped because that is after, what did we say, 10 seconds. Okay, so if you change your Tmax to a larger number, it would keep on going. So there, that's cool. Last one. This is the problem I know you've been looking forward to. Mr. Vranick, Mrs. Delzati, and Mrs. Stites are all racing. When the race begins, Mrs. Stites is accelerating at a rate of 1 meter per second per second. Mrs. Delzati is running at a constant rate of 5 meters per second. Mr. Vranick trips and falls and starts running at a constant rate of 6.5 meters per second, 3 seconds after the beginning of the race. Oh, Mr. Vranick. The race is 100 meters long. Who wins? What are the 3 places? Oh, this is so dramatic. So, all right. We're going to need 3 sets of equations. Stites. Delzat. And Vranick. Okay, for the heights, I'm just going to do 1, 3, and 5. Oh yeah, and so again, the purpose for that, you can see the separation between them. I mean, I guess you can put one on top of the other, but depending on your window, like if I had this at 2 and your window is different, they'd just be really smushed. I like a little separation. So, okay, let's see here. I accelerated at a rate of 1 meter per second per second. Acceleration, so 1/2 AT squared. Delzati, constant speed of 5 meters per second. Okay, that's distance equals rate times time. So I'll write these off to the side for you. So she's just a 5t. Notice she didn't fall or anything like that. And so she's still a t. It is Vranick who trips and falls and starts 3 seconds after. So he's been traveling for 3 seconds less. He's still a constant rate, so rate times time, but he's a t minus 3. All right, we are going to have to change our window again. And if you just want to watch this because you don't want to be spoiled, I'm okay with that. .5. All right, so I'm up to 5 now. Let's see. Because I have done this problem before, I'm going to make our Tmax 30. I just know that we will get to the 100 meters in that time. T-step will keep at 0.05. So x-min is 0. My x-max, well, the race is 100 meters long, so I'm going to put that as 100. Oops. Let's try that again. X-max 100. And I'm going to make my y-max 7. Okay. All right. Again, y-max 7 because that's a 5, so I'm going bigger than that. Okay, so reminder, Stites is at 1, Delzati is at 3, Vranick is higher up at 5. Okay, here we go. All right, Stites and Delzati start at the same time. Vranick just started because he fell. Oh, this is so dramatic. The 100 meters is the end over here. Who's going to win? Oh gosh. Oh, I'm pulling ahead, you guys. This is a shocking development. Oh, Mrs. Stice is going to win the race. This is brilliant. Let's see who's going to come in second. Vranek has picked up the pace. He had a higher rate. Vranek in second. Mrs. Delzati in third. So who wins? Stites, obviously. Stites is first. Vranek is second. Delzati is third. Don't tell Delzati. I don't want her to hurt me. So there you go. There's your parametrics lesson. I hope this was enjoyable to you. The first page, this is going to be more important for your test, but I think these problems on the back are really cool, especially visually, and so that's why we spent some time doing them. So the homework for this is day 14. And most of the problems are pretty similar to what we just went over. There are actually only, there aren't that many questions. There are like maybe 5 of them. And you know what? I'm going to cut a problem because I'm feeling generous. You can cut number 57. It should be the very last problem on the homework. So 57 you can cut, and that means that you only have 4 problems to do. Hooray! So tomorrow is review, and then Wednesday is the polar vortex. So let's just assume your test is Thursday or Friday. Okay, we're going to assume that. And as each day passes and we see where we're at, whether we'll be at school or not, you will get more information about that. But review tomorrow. Please let me know if you have any questions. You'll definitely get folders back tomorrow so you can look at all that stuff. And if we do happen to have days off later this week, you can work on your reviews. Feel free to email me and ask me questions. I can post some videos. But tomorrow you definitely want to look at folders because, you know, you can't take those home. So, all right, have a great snow day. See you later.